what we really needed for this to work, okay? So will this always work? And the response to that is, well, we'll see, okay? So given some initial boundary value problem for u of xt, right? The main idea is as follows, right? So if we find all solutions, right, of the form xt is equal to vn of x and wn of t, and in this case we had n equals 1, 2, 3, and so on. I'll just say that lives in that set. Okay, and then vn of x need to satisfy our boundary conditions, okay? I mean, there's a few things that could have happened here. We could have had inhomogeneous boundary conditions, so we'll have to talk later about how we deal with that. Because we had homogeneous boundary conditions, everything worked out nice because the homogeneous boundary conditions just get inherited by the basis functions. That's not going to happen if we have inhomogeneous boundary conditions. Okay. And also another crucial thing is that to satisfy the initial condition, right, we had this sum n equals 1 up to infinity of bn un xt, right? And we chose bn to satisfy the following equation, right? So the sum from n equals 1 up to infinity now, we selected wn of t to just be 1 when t equals 0, right? So then our boundary condition, or sorry, our initial condition just became this, right? This equation here, that I need that infinite sum to equal f of x, okay? And the point I was making before is that for this to work, we need what's called completeness of the set v n of x n equals 1 up to infinity over functions satisfying our boundary conditions, okay? And what else do we need? We need some method for obtaining the bn that we got, right? And this really relied on the orthogonality of vn of x, okay? What's the problem if we don't have completeness? Well, then we could have functions that, you know, technically satisfy our boundary conditions, but we can't construct them. If you don't have a complete set on the space of functions that you're trying to represent, there are going to be functions that you can't represent, okay? If we don't have orthogonality, right, we're going to have this infinite, essentially matrix equation for all of our bn's, and it's going to be dense, right? It's not going to be, we're not going to be able to diagonalize, right? And essentially what we were able to do is diagonalize this system because of the orthogonality of Vn, okay? So that's how this all fits together, right? So that's what we need. So what we'd like in general is some condition for knowing when we're going to have a complete and orthogonal set of eigenfunctions that satisfy our boundary value problem. And that's what's at the heart of what's called Sturm-Liouville theory, which we'll get to maybe in next lecture. Okay. So so let me circle back, okay, now to our original initial boundary value problem. So this apparently had the properties that we needed in order to get sort of a well-behaved set of eigenfunctions, right? So u of x, right, is equal to the solution that we derived, right? Sine of n pi x over L, okay? B n is equal to 2 over L, integral from 0 to L, f of x sine of n pi x over L dx, okay? Now, we derived this solution. We sort of took all these integrals. We did things that were legal and correct, okay? But we still need to check, right, whether this actually satisfies the boundary conditions and the initial conditions, right? Now, of course, you know the way to do that is you can plug this back into your PDE. You can plug it into your boundary conditions. You can plug it into your initial conditions, right? Okay. So let's go through that process, right? So does U satisfy the PDE? Okay, that's worth asking. Well, U sub t, right, is going to equal this infinite sum, n equals 1 up to infinity, b sub n, and then when we differentiate this, right, we're going to get a minus k n squared pi squared over L squared coming down, and e to the minus n squared pi squared L squared t sine of n pi x over L, right? When we compute kuxx, right, we're just going to end up differentiating our sine function twice. And so again, we get, well, I'll bring the k inside to make this a little more transparent, right? I have an n pi over L, an n pi over L, right? An e to the minus n squared pi squared over L squared t. And now this has become a minus sign, n pi x over L, right? So minus times, n pi over L squared times k is equal to this, okay? So that checks out. Indeed, that ut is equal to kuxx, okay? So it does satisfy the PDE, okay? Does U satisfy the boundary conditions, okay? Yes, I'll go ahead and say it. Because u0 of t, right, is going to be equal to the sum from n equals 1 up to infinity, bn. But now we're evaluating the sine function, right, at 0, right? So I have bn e to the minus n squared pi squared over L squared t times 0. And I can add up as many zeros as I want, and I get 0, okay?
Professor?
Yes.
Where did k in ut come from? In the ut expression for ut, where did the k come from?
Sorry, I dropped my k here. There should be a k up here, right? Because there's a k up here.
Okay.
Because when we solved for our w of t, right, we had a k, we had like minus k times the eigenvalue. So you always get this k up here in the t part of the separated variable solution. Sorry, I dropped the k before. The k up here. Thanks. Other boundary condition, right? God, I keep dropping the k. Sorry about that. Minus k n squared pi squared over L squared t, right? But sine of n pi, right, for any n is going to be 0. So again, we get 0. So yes, it satisfies the boundary